Good afternoon. I'm Donna Guerin, Executive Vice President of Science and Policy at the American Frozen Food Institute. Welcome to today's webinar, the fifth and last webinar in the Sanitation Controls track of AFFI's Food Safety Webinar Series. During today's presentation, we will explore cleaning and sanitizing chemistry with Mark Kasich of Ecolab. Do appreciate Mark being on with us today. His colleague, we've often worked with Ecolab in creating many of our recommendations, most recently with your colleague Rick Stokes, who led our sanitation working group that, again, led to many of our recommendations on our AFFI food safety website that was recently created and launched in February. So I'm going to give you a little bit of background about Mark and his role. So he is the Senior Area Technical Support Coordinator at Ecolab. Mark has 45 years of food industry experience. Mark's areas of expertise include fruit and vegetable, red meat, poultry, ready-to-eat environments, equipment design, processed foods, snack foods, cereals, and wet and dry sanitation. Prior to Ecolab, Mark was the corporate sanitarian for Jenny O Turkey, or Hormel, and we're pleased to have him join us and give a little bit of background on the chemistry associated with cleaning and sanitizing. Before we go into today's presentation, I would like to turn it over to Sarah Brandmeier, our Manager of Scientific and Regulatory Affairs here at AFFI, for some housekeeping information.
Thank you, Donna. So we will not be answering questions until the end of today's webinar. However, throughout the webinar, you may write your questions in the text box on your GoToWebinar control panel, and Donna and I will read them aloud during our question and answer session. And also, this webinar is being recorded, and the recording and presentation slides will be distributed to all of you in the coming days. And we are excited to have you with us, Mark. So with that, I will turn it over to you.
Well, thank you for the opportunity to share this presentation on cleaners and sanitizers. Next slide, please. The agenda for this presentation will cover three areas: provide some background and definitions, review the 5 factors of selecting a cleaner and the basics of cleaning chemistries, and choosing the right sanitizer. Next slide, please. And we're going to start with cleaners. Next slide, please. The whole purpose of the sanitation process is to remove soils, and there are 2 basic types of soils: those we can see and those we can't see. Since we're discussing cleaners in this section, and we are looking to remove those soils that are visible during the sanitation process, we're going to be looking at those visible soils that we're going to remove with cleaners. Next slide, please. There are actually 5 key factors that are used to choose the right cleaner. The type of soil or nature of the soil is one of the determining factors when choosing a cleaner. The characteristics of the water, like water hardness or iron, silica, minerals, pH, can determine what cleaner can or cannot be used when cleaning and removing soils. The material the surface of the facility is constructed with, or the equipment is constructed with, whether it's made of stainless steel or soft metals or plastics or rubber, that all influences the type of cleaner and the choice that you make. The method of the cleaner, how it's applied, whether you're going to manually apply it, whether you're going to foam on the cleaner, whether you're going to apply it through a clean in place application or a clean out of place COP application. And then there, of course, are the environmental guidelines that all of us now are becoming more and more concerned with. Whether a chemistry has phosphates in it, or whether there are solvents that restrict the use of certain chemistries. These chemistries could harm fish or wildlife. They could pollute our water source, and that's of great concern for us. Because of the time that we have, we can't talk about all 5 of these, so we're going to focus primarily on the nature of the soil. Next slide, please. So, what soils are you cleaning? What effect is needed to remove the soil? What chemistry will deliver the desired action? Next slide. Soils come from every conceivable source you can imagine, our food processing facilities. Obviously, from the product we manufacture, it can be left behind when water dries. It can blow in through our open doors and carry through the facility because of poor airflow control or even poorly controlled air intake systems. Our employees are a big source of soil loads, and they can carry them in on their clothing or on their shoes. It can be left behind due to poor sanitation practices. If chemistry dries on the equipment, the chemistry that you use to try to clean equipment, if it dries, it becomes the soil. And it also can be the microbial load that grows because of poor quality controls. Soils can come from any source. Soils are any unwanted matter on any surface that needs to be removed before sanitizing. Next slide, please. There are 4 basic soil types: fats and oils, carbohydrates, proteins, and minerals. Our food products are made of one or a mixture of these types. And our processing, whether through temperatures or through the processing times that we run our products, have an effect on the soil characteristics. Because of these soils and the blends of soils and the processing methods, our soils become complex. Cleaners can be built to address these changes to enable the removal of these soils. Next slide, please. Here are some common foods and a breakdown of the soil types of each. All have different levels of fat, protein, carbohydrates, and calcium, which would determine which blended chemistry would be most effective in removing the soil load. Next slide, please. Besides the soil type, we also talked earlier about what effect is needed to remove the soil. Do we want to dissolve the soil? Do we want to liquefy it, hydrolyze it, disperse it, emulsify it? Each one of those ways is a way of breaking down the soil, removing that soil. And I won't define each one of those right now, but we'll talk about each one as we go through the information coming up. Next slide, please. You know, the end result, the goal, is always a clean surface, ready for sanitizing. Next slide, please. So now we're going to get to chemistry. Which cleaner are we going to select? Is it going to be an alkaline, an acid? Are we going to use an oxidizer, an enzyme, a solvent, a surfactant? Well, we don't know, because we have to look at the type of soil that we're going to deal with. And as we look at that, we're going to look at to see what characteristic we have to use and what effect it's going to have on that soil. Next slide, please. Alkaline cleaners have high pH ingredients that disperse or dissolve organic soils by charge repulsion. They use their electrical charge to help attach to soils and remove the soils, to break up the soils. Next slide, please. Protein soils have molecular structures that are long and complex. The addition of oxidizing agents and enzymes break up the protein molecule into small particles that are more soluble for removal. Next slide, please. Oxidizing agents like sodium hypochlorite, bleach, breaks down protein molecules, as seen in this chart, easier than if just using an alkaline chemistry such as sodium hydroxide. A reduction in the concentration of the alkaline chemistry is also measurable. So you can see in this chart that if I just used an alkaline chemistry, it takes not only a higher concentration, but it takes longer to get a more percent dilution or breakdown of the protein molecule. But if I add a oxidizing agent to that alkaline chemistry, so using a chlorinated alkaline chemistry, I can reduce the concentration and still have a better reduction or a better breakup of the protein. Next slide, please. Enzymes, on the other hand, work by unlocking the bonds that hold proteins together. Enzymes are effective where oxidizing agents are not recommended because they damage equipment or components of the equipment, like a membrane application. If we used chlorine in membranes, we would actually damage the membrane. But enzymes are more effective, and we don't have to damage a very expensive membrane system. Next slide, please. Solvents are particularly useful removing fat and oil soils. But the concern in a food processing environment is, does the solvent have an odor to it? Does it rinse freely? Is it biodegradable? So we want to make sure that our solvent is functional, but it doesn't have the concerns that will give us other issues. We don't want to solve a problem by creating another problem, but solvents do help in removing fats and oils. Next slide, please. Surfactants, they're very interesting. Surfactants are critical components in many cleaners. They reduce surface tension of water in cleaning solutions. They kind of make water wetter, so to speak, allowing cleaning solutions to penetrate into cracks and crevices. They help improve the soil particles to get into the cleaning solution. They improve the rinsability of the cleaning solution and suspend the soil into the cleaning solution so that when it does get rinsed, not only do you rinse the cleaning solution away, but you also rinse the soil away. Next slide, please. Solvents also help in creating foam. We talked about earlier about how you're going to apply your chemistry, whether you're going to foam it or manually clean it. And in foaming it, you want to make sure that you get a good cling, a good foam, a good dwell time, a good contact time. In that picture on the left, you can see that foam as it clings to the surface. As long as it holds on to that surface, it's giving you that contact time so that chemistry can contact that surface and keep it and continually clean it. If it just rolled off of that equipment, if it didn't hold on to that equipment, it wouldn't give you much contact time, much dwell time. And then, of course, everybody that uses manual cleaning, they like to see the foam. It helps hold the soil in suspension. And then, of course, in CIP, in clean in place, you don't want foam. So even in using certain surfactants, you can control not having foam by the reduction of it. Because if you have foam in a CIP application, where you have the pumps and you have the flow of the cleaning solution, you'd have cavitation. You would have huge application of generation of foam, and that's something you certainly wouldn't want. Next slide, please. Surfactants work to emulsify organic soils like fats and oils that do not mix with water. We know that water and oil don't mix, but we still need to get that oil off of our surfaces. So how do we do that? We use a cleaner that has surfactant, and the surfactant then attaches to that oil. And as it attaches to that oil, it allows that oil to suspend in the water. It doesn't mix, but it allows that oil to emulsify and hold in suspension so that as we go into the rinse step, we can carry the oil and the fats out with the cleaning solution. And that's how we want to do that. Next slide, please. Here's kind of a little experiment, and it's obviously much cooler to see in person than on a slide. But on the picture on the left, you can see a red bead in that glass of water. And it's just kind of resting there. It's kind of sitting, floating, and it's not mixing. But the minute that a surfactant is added, that red drop, that red bead, just emulsifies in the water. It mixes. It breaks apart. And you can see where it would be easy then to take that bead that's so difficult to control, and then you can break it into, suspend it into solution and be able to move it easier. Next slide, please. Surfactants can also help in reducing the temperature to liquefy fats during the sanitation process, which helps food processors in a couple of ways. Some food processors have a very difficult time achieving hot water requirements needed to liquefy fat. So how do you liquefy fats if you can't get the temperature of your water hot enough? Well, one way is to add a surfactant or have a built product that already has a surfactant so that you don't have to use as hot of a temperature. Another thing that benefits is if you have a sustainability initiative with your company. In other words, you're trying to reduce your energy costs. By having a built product that has surfactants built into your product, you can reduce your energy costs because you're not raising the temperature of your rinse water, your initial rinse water to liquefy your fat. So you can use a lower temperature rinse water, saving energy costs, fuel costs, and that helps in your sustainability initiative. Next slide, please. Then there are the extreme complex soil conditions that require cleaning procedures to max their complexity. So often we produce products that are just so filled with ingredients that are just so difficult to clean. And these difficult ingredients just attach onto everything. And because we still have to get everything clean, we have to come up with a way. We have to come up with a means, with a chemistry. And it's very difficult. Burn-on soils due to procedures, processing failures, makes it very difficult as well. Sometimes our process just doesn't work the way we want it to. Next slide, please. And in this slide, you see those issues. You see the denatured protein in the slide on the left, where the product is actually just burned on. Those are really tough soils to remove. And then you see the carbohydrates burn on in the picture on the right. Very difficult, but we still have to remove it. We can't start up the next day with soils like that. So we have to come up with an answer. And the answer may not be the same chemistry that we use every other day. Maybe this is every other day. Maybe this is our normal process, so we do have chemistry for it. But maybe it's because today we had a problem, and now we have to come up with an answer. So what is our answer? We have to come up with something. Next slide, please. Complex soils need advanced cleaning programs or advanced chemistry to address the complex soils, as in shown in this slide of an acid-alkaline override or a peroxygen-alkaline override. In both cases, a chemical reaction is used to break up or pop the soil from the surface to remove it. It's a different type of thought process. It's not that you're attacking the soil in the conventional way. You're actually using the chemical reaction of the two opposites to actually make, let's say, mini explosions to pop that soil, many chemical reactions to break that soil and to break it away from that surface. So whether the soil is simple or complex, Choosing the right cleaner is important to reach the goal, a clean surface ready to sanitize. Next slide, please. So we're going to talk about sanitizers. We've got our plant clean, and that's a good start, but we still have more to go. Next slide, please. This time we are removing the microbial soil load from our food processing equipment, the invisible soil, and we have to know which is the correct sanitizer to use. Next slide, please. And in deciding, what sanitizer to use, we want to understand what is a sanitizer and what does a sanitizer do. We want to look at what is not a sanitizer. And a sanitizer is not a sterilant. A sanitizer is not a disinfectant. And many times when we talk about sanitizers, we kind of mix up the term and we get a little confused sometimes. And when we talk about the sanitizing steps in the sanitation process, a sanitizer reduces the microbial load to what is considered a safe level and provides a 5-log kill. Next slide, please. It should be noted that some food processors do use peroxy acids and chlorine dioxide as sanitizers, but in concentrations much lower than what is used for sterilizing. Next slide, please. There are many effective methods for sanitizing, and that have specific applications other than chemical sanitizing. However, since this presentation reflects the chemistry of sanitation, we need to talk about the chemical side of the sanitizing spectrum. So sanitizers are divided into 2 types. Chemical sanitizers are divided into 2 types. No rinse food contact surface sanitizers and no food contact surface sanitizers. Next slide, please. Every method has advantages and disadvantages, which must be assessed by the food processor. In chemical sanitizing, the advantages is the efficacy and the penetration. Because we've got a liquid, the penetration is great because the liquid can flow. Disadvantages, we've got chemical safety that we have to make sure that we can control. And obviously there's the cost. Next slide, please. So how do we choose the right sanitizer? What microorganisms are you concerned about or trying to control? What are the commonly used chemical sanitizers? What factors affect efficacy? Next slide. Microorganisms have a broad spectrum from bacteria to yeast and molds. There are many methods used to detect and analyze microorganisms. Next slide, please. Pathogens create the greatest health risk to consumers, and food processors are diligent in ensuring their facilities and equipment are controlled and that they maintain strict controls over these pathogens. Next slide, please. The understanding of biofilms, how they form, how to destroy them if they do form, how to prevent them from reoccurring has become more and more prevalent in the sanitation process. I can remember when we first started talking about biofilms, and it was really foreign. I mean, not only foreign, but it was almost, if you weren't, it was almost like hocus pocus. I mean, you know, what are they trying to sell us now? You know, but the more that you get into it, and the more that you understand it, and the more that you understand how they're developed, and what really occurs, and then in trying to remove them, the more you understand how you can actually create a bigger problem by not getting totally rid of the biofilm, the more that it's important to really be able to go after the entire biofilm and to eradicate it from and control it from your program. Next slide, please. So the most commonly used categories of sanitizers are chlorine, quaternary ammonium, peroxyacetic, fatty acids, iodophores, acid anionic, alcohol QUATS. Next slide, please. Each of the sanitizers have advantages and disadvantages. And I'll go through each one relatively quickly. Each has the concentration range that is on the label and must be followed and is approved for its legal use. All sanitizers are regulated by the EPA. All, if used below the concentration range, are ineffective, and all, if used above the concentration range, are being used illegally. Some are more effective on specific microorganisms than others. And the fact is, there is no perfect sanitizer that fits every application. Sanitizers must be matched to the environment and the microorganism that it's being used to control. So we look at the first one, the chlorine, the sodium hypochlorite. It's relatively low cost. The spectrum of antimicrobial activity is broad. But the relatively low cost is kind of a misnomer, because if you look over on the other side, the disadvantage, it's very corrosive to stainless steel. It's extremely corrosive to soft metals. So what might be inexpensive in its initial cost might cost vastly in the damage that it does if it's not handled properly. And then if it gets in contact with organics, it dissipates, it's inactivated. If it gets into heated temperatures, it gases off. And don't ever mix chlorine with acid. A chlorine gas is produced and it can be deadly. Next slide, please. Quaternary ammoniums. They're excellent for environmental sanitation. They provide a residual antimicrobial activity that lingers and gives you a little bit of masking onto your equipment or onto your environmental structures. They're non-corrosive, but what they're not good in areas where there's fermentation. Next slide, please. Peracids, peracetic acid, and peracids. Broad spectrum antimicrobial activity. They can actually, if used properly, give you a one-step acid rinse and acid sanitize, all in one step. The disadvantage is they're very corrosive to soft metals. And some people find the odor very offensive. Next slide, please. Fatty acids, low foaming CIP application. There again, that CIP application, making sure that the low foaming application is important. Again, the broad spectrum of bacterial activity, the removal and control of mineral films because of the acidic. On the disadvantage, the pH sensitivity, the optimum activity very low at that less than 3.5. And then do not use at greater than 100 degrees Fahrenheit. So in a CIP application, you might go higher than that 100 degrees, and it wouldn't be very good in that application. Alcohol quat, extremely good for areas where water sensitivity is not wanted. They're quick drying. They're great for production changeovers. They're great for areas where you're doing dry cleaning. They're non-corrosive. They're excellent for environmental sanitation. The problem with them, the disadvantage, is it's all manual sanitizing. And there's the flammability rating that you have to deal with. Next slide, please. The iodophores, they have their benefit, but they're very high in phosphate. So if you're in a phosphate-free situation, you can't use an iodophore. And sometimes you don't like the color. You don't like that red, orange color, brown color. Acid anionics, the great one-step acid sanitizing rinse. And the disadvantage, high in phosphates. And the foaming in CIP. Next slide, please. This graph emphasizes the whole process where the sanitizer has to be matched to the environment and has to be matched to the microorganism that you're going after, whether it's a gram-positive bacteria, gram-negative bacteria, yeast and mold. It's very important that you can see where the certain sanitizers are much more effective than others, and you have to decide which one you want to use for your application. Next slide, please. So hopefully this whirlwind tour through chemistry of sanitation, cleaners and sanitizers has provided you with some very basic information of why some chemical products are used over others. There's so much more. We could talk for hours on this subject, but trying to encapsulate it into a small time period is sometimes tough, and you know, you leave so much out, but it starts the discussion anyway. Do we have any time for questions? Any questions?
Yes, we do. Thank you, Mark, for that excellent presentation. I would like to officially open the session for questions. Again, you may write your questions in the text box or on your GoToWebinar control panel, and Sarah will read them aloud because it's way too small for my eyes. So we actually do have a question already waiting for you, Mark. Sarah, you want to read that?
Yep,
okay.
I will. Thanks, Donna. So Mark, the question is, the asker is wondering what information you have regarding a microorganism forming a resistance to certain sanitizers. And would you recommend a sanitizer rotation program for food facilities?
That question has come up a lot. And there is a lot of talk back and forth. Some view that there is some resistance, and others believe that there isn't. This is how I look at it. What I do is I believe that it's okay to do a dual sanitizing process. In other words, if you sanitize, say, with you come in with a oxidizing sanitizer, and then you come back with a peroxyacetic acid sanitizer, and then you do your environment with a chlorinated, not a chlorinated, but a quaternary ammonium sanitizer for your environment. That some people do that. I guess what the question is, if you use a chlorine one day and a quat another day, and then you use another sanitizer another day, so that you can kind of trick the microorganism so that it doesn't become mutated, so that it doesn't become immune to the sanitizer. I believe that there's documentation that says that does not happen. The key is to use sanitizer at its prescribed concentration. If you use a concentration that is below the recommended limit, yes, you will damage microorganisms and they will not die. So you have the possibility of changing the microorganism so that it's not going to it's going to have some kind of resistance, but because you didn't kill it in the first place. But if you use sanitizer properly, I don't see that's going to happen. I'm not a microbiologist, I'll tell you that up front. But the microbiologists that I have talked to, they say that microorganisms do not develop an immunity to sanitizers. So it's not necessary to switch off, but it's okay to switch off just to make sure that you're getting the full spectrum of the microbial growth that could be within your facility. So that's kind of talking about things differently. I don't know if that totally answers the question, but that's the answer I've got.
That's great. Thanks, Mark. I think we have a couple more questions that we have time for.
Yes, we do. So, Mark, the next question is, with norovirus and Hep A in the spotlight, what sanitizer would you recommend to control viruses?
Well, people need to wash their hands. People need to, it's not all about what sanitizer. We have to make sure that we have clean environments to begin with. Everybody points the finger at the sanitizer and expects the sanitizer to do all the work. We have to get the surfaces clean first. And you notice in the whole process of this presentation, it's first about getting the surface clean. And part of the cleaning process is removing the soils. And you will remove microorganisms during the cleaning process. You won't remove all the soils, but or all the microorganisms, but you will remove many of them. So it's important to make sure that the surfaces are clean first, and then making sure that you use the right sanitizer. Now, as far as which sanitizer, that's kind of a different area than that I'm in. That's more of a we're getting into the viruses, and that is not in the area of food safety that I deal with, but I would certainly look at the peroxyacetic sanitizers, the chlorinated sanitizers. But I'm sure that things like institutional groups and hospitals would have other types of sanitizers that would be used for their applications outside of the food processing area. Does that answer it?
Yeah, great, thanks. We're going to combine a couple of questions since LM is tends to be our pathogen of concern, and we have below zero environments. So, Sarah, you want to read it?
So then what chemical or chemicals would you recommend that best addresses Listeria pathogenes in the environment, as well as in the processing area that's operating in a frozen environment?
Well, LM doesn't like acidic environments. So anything like peroxyacetic or any of the acid sanitizers are all very good for that type of sanitizing. Anytime you can reduce your pH is excellent.
Okay, great, thank you. So our last, how often would you recommend that advanced cleaning takes place in the case of removing a complex soil buildup, and how?
I'm sorry, you're breaking up.
Okay, I will say it one more time. So how often would you recommend that advanced cleaning take place in the case of removing a complex soil buildup, and how would you prevent this complex soil buildup?
Okay, well, the truth is in the numbers. So the numbers are your swabbing and in your micro counts. So if in your product shelf life or in your environmental swabbing program or in your equipment swabbing program, if you're not able to control your micro count. I mean, because you know, a lot of companies have gone to extended cleaning, and their runs might be for longer than a day. Could be 2 days, could be 20 days, any extended period of time. Whenever it affects the quality or the food safety aspect of the product, or if it affects the processing, if you're running your application or your product and you know you're supposed to get X amount of pounds out through your line, and all of a sudden your line runs from 20,000 pounds an hour down to 5,000 pounds an hour, you know you got to clean your line because your output is not there. So you know you have to look at that. But I always look at you've got to look at your numbers. If you can't control your micro load, then you've got to clean more often. If the quality of your product, if your shelf life is not lasting, you've got to clean your equipment. If you know if you've got black specks in your product that aren't supposed to be there, you've got to stop and clean your equipment. And then you've got to keep record of that so you can determine how long you can go before you have to stop and clean. I know in so many of our facilities, everything is production orientated, and you know that's where the money is made. But I think people are kind of finding out that sanitation is important, and even though it's not a profit center, it can certainly add to the profits if things are maintained properly, and if sanitation is put into the schedule so that it can keep the operation running at peak performance.
Okay, great. Thank you so much, Mark. I want to thank you again for sharing your time and expertise. And I also want to thank all of the attendees of today's webinar for joining us today. And as was mentioned previously, the webinar slides and recordings will be shared with all of you in the coming days. So we do hope that you will join us for our next webinar, Microbial. Registration information for all of our webinars can be found on AFFI.org as AFFIFoodSafety.org. So thank you again for joining, and I hope you have a great day.